Cleaning Blackboard, let me come back to the question of you, of Daniel. So indeed, we heard also this question from, similar question I think, from Reinhard Wenner, who complained that this commuting with the total Hamiltonian is too rigid. So he said that what we should do is we should allow for some tight, small violations of energy conservation, and this is really some physics that one has to do, and I think it's something that we've for a while there was a lot of simpler stuff to do, but ultimately we have to make hands dirty and go into this, I think, but that's a difficult project, so yeah.
So but then why the energy is not conserved?
No, it's just for the purpose of accounting, because of course in the universe energy is conserved, but now if we want to like do some thermodynamics, then we should account for energy. So in principle we don't want that energy is, we want conservation of energy in our, say, our operations shouldn't add energy. But because if you have a real physical heat bath, and so then you essentially would have, for example, continuous spectrum, and you also when you try to even to so let me say this: if you try to justify the approach, you essentially what you have to do is you should consider the global system with interacting Hamiltonian, and you have some, say, your working body is actually brought to the contact of the heat bath, and then it goes away. So this should be described somehow like in collision theory picture, and then you have to. Sorry.
What you describe is time dependent.
It's even time independent, because you can consider it just that it just goes. It's like it's time dependent when you really bring it, but finally you can describe it as a full thing, like time independent, like the particles that are scattered. Yes, they have some initial state that is asymptotic state, then there's interaction stage, and then you have another asymptotic state. And what you are interested in is this passage from some asymptotic state to other ones. So you have to do very carefully this collision theory, and this we didn't do for a while. So, and then you have to, then you will not have any such very rigid conditions. You have to, then you will see in order any evolution, for example, to start with, you have to have even very far away from your interaction. You have to have some slight interaction, yes, because otherwise nothing would happen at all. So therefore, you will have you need some slight departure from the very rigid thing. I'm hand waving now, but yeah. So indeed some physics will need to be done. Good. So then, so I will today try to continue with Thermo for kids, and then hopefully go to adults. So I recall what I said yesterday, that we define operations. These are the noisy operations. Okay, and then I will tell about single shot loss of transformations, or of state transformations. So I already said this fact, so I will repeat it then. Then I will say about IID limit. So here was single copy, here many copies. So in this IID limit, so here essentially we have irreversibility, and here we will have reversibility. So here here we will retain something that we know we have in thermodynamics, and then I'll talk about extractable work and work of formation. So so that was actually, we didn't consider it in our old paper, so that was considered, especially this work of formation was never considered, but this extractable work and some other things were considered by and I think there was also Renato and Vlatko, 3 persons. In this paper, so I will also plus smoothing of course, and there was also a last thing that I maybe will not talk for Thermo for kids, because from my point of view it's more maybe somehow more natural to talk about it for in the other part of the lecture. But let me just say that in the paper by it was just, I think, this. No, it's just. So again, here at so there was, yeah, again, Renato is there, Jonathan and Oscar, Dalston and Philip Feist, yes, here, and Dupuy. Good. So that's the, so what they consider here. I guess what I can write it like that. I guess this thing. I guess you considered. I think so, and also reference. So in this lectures, I will not touch the issue of that I operate on some system, but I want to preserve correlation with some reference. So I'm only concerned with the system itself. So I'm interested in this to be changed, and I apply of my operations to the whole system. But you can be more detailed. You can ask more general questions. You can ask that I want to go from this state to this, but you can only operate on this system. So the previous paper was Del Rio with again Renato on the board and Vlatko Vedral, I guess. So there this question was kind of was posed, and then and also in this paper. So right. So I will mostly talk about these things. I already yesterday said about this so noisy operations and of course single-shot loss of state transformations. So we asked, so there was this fact, let me call it now fact 1, that rho can go under noisy operations to sigma if and only if rho majorizes sigma, and I defined majorization. Maybe I should write it so that, because I will refer to it more often. So majorization. So we have that this P majorized Q if and only if, and I take this partial sums of the ordered distributions. So that's okay. So that's fact first, and then how one can get it by 2 facts. So first fact is a so let me just maybe give example for this majorization. So 2 examples. So first, for example, if we have just 2 just binary probability distributions, say, but then I have collision. because by this I denoted the full probability distribution, and here so when is this? So when this majorizes, so here the condition is very simple because majorization is just about, so because we have just only two sums, so we have only L is equal 1 and 2, and therefore the first sum is that simply P is greater than Q, and the other sum, so that's for L equal to 1, and for L equal to 2 we have just P plus 1 minus P, Q plus 1 minus Q. So we have something that we know already. So that's the only condition in this case, but already in, so here is the picture, yes, so this is more mixed than this. So if we say this majorizes this, we can also say that this is more mixed than this. So this is this thing, and if you have three probability, three elements, then you can also nicely represent majorization as Q2, Q3, where you simply say first the same thing. So let them be already ordered. So usually when I already write ordered. Okay, ordered. So P1 should be greater than Q1, and then the other condition, the second only non-trivial condition is this. Q1 plus Q2, but you can see that it is 1 minus P3, 1 minus Q3. So ultimately you obtain that it is P3 must be less than Q3. So the largest probability should be greater, but the smallest should be smaller. So essentially it is this picture. Yeah, and you have this thing, and then you have, so this must be larger, and this must be smaller than this one. Good. So now, and also what is maybe good to note, to point out, is that the majorization can be seen as that one function is greater than the other function, namely, maybe not a function, but you can write some cumulative, histograms. So these are histograms where you just put probabilities, and now you can put the sums. So that's the first thing. Then you sum up, so you get this thing, and then you finally do this. So that's some. That's fair. These are these partial sums. So first sum is here. It's just the largest probabilities element. Then you have two largest, and then you have all. So you can now simply write these two probability distributions on the same. This cumulative, let's say diagrams. You can write on the same on one reference frame. So then you get this thing I draw here, then I add, which is say here, and then maybe like this, and finally I obtain the sum of three of them must be the same because they all both sum up to 1, and then you see that simply majorization means that you can draw such curve, and then you draw this upper curve. So you see that the majorization means that this curve is above this curve. Always. No, not always, but just for these two probability distributions.
Does that imply so rho is being taken to some is a state and it's being taken to some other state, sigma, under this noisy operation?
Rho is taken to sigma by noisy operations, yes.
And what is the what is this? What is the fact that rho majorizes sigma imply?
That spectrum of rho majorizes sorry. So this fact is when this, which by definition is that spectrum of sigma majorizes spectrum of rho majorizes spectrum of sigma. This is eigenvalues. So you just apply therefore this whole picture. You just this p, This P, say, is a spectrum of rho, and Q is spectrum of sigma.
So this was for the trivial Hamiltonian.
Yes. Yeah. Good. So, okay. So then, how to see that it's true? So you simply take fact 2, which was proven somewhere. People know it. Namely, if P majorizes Q, if and only if there exists a how to fact 2, if only if there exists a channel, a mapping, or let me say, where is it? Okay, let me write it like that. There exists a channel such that it gives Q, and the channel is a mixture of permutations, convex combination of permutations. So, so an example is that you have, suppose you have two-level probability distribution, this thing, and then you let me make the following example. Aha, good. So that's the one thing. Then you permute it. Okay, so you simply change the so you consider permuted one, and then you mix them with some weight. Right. So you so you finally get some. So what happens is that altogether it becomes more mixed. So if you do that, so let me write it symbolically like this. Then you get something that is so let lambda be greater than half, then it will be something like this, right? So we'll see that this goes a little bit down and this go up. So what happens? What this operation can do, it takes the original probability distribution and it takes this portion and puts it here, up there. This is what happened here. Yes, this portion was put here. Good. So that's an example of such operation, and we see here from this example that indeed this original probability distribution, indeed it majorizes the final one. Yes, because we see this probability is larger than this one. So one can how to see this fact. So in one direction, suppose that so let's say this direction is kind of easy. Here was an example, and more generally you simply do this. You have this distribution P. You have the distribution P, and then you have the distribution Q. You have the distribution P, and you have some permuted distribution. Yes, so you permute. Okay, and what is true is that every such partial sum have to go down or cannot go up, because you simply suppose we consider a sum from I to 3, and we mix these, and finally, so we mix this with lambda minus 1 minus lambda, we mix them, and then we see that, for example, suppose we don't know which one will be now the largest one, because after mixing we have to order it. So a priori we don't know what will be the because we don't know what will be the resulting probability distribution, then we don't know which one will be the largest one. But suppose these are these one. Suppose by a chance that these are these one. These are So if we mix them, we will get with this weight, we will get this will be the first, second, and third largest. So then you see that this sum is actually a convex mixture of this sum and of this sum, right? So this will be a convex mixture of this first sum. So let's say some like of this and of this. So but you see that this sum here, it cannot be, it is definitely not larger than the largest possible sum, which is defined by this, because this is the largest possible sum of three elements. So this may be only smaller, perhaps equal here also. So each of them are less than really this original largest PIs. So therefore, if you mix them, it's also smaller. Right. So this is when you have just mixture of two, but any convex any permutation you can combine with combine out of sorry what I said is it's enough to consider these mixture of two elements. Right. So this is in this direction. In the other direction, I will also give some very hand-waving argument just to see that, just to have some flavor. What happens is that, so suppose I have some probability distribution, and I want to go to some probability distribution that is majorized by it. Okay. So then what I can do is I can say, oh, first let me make this guy. This I have actually. This I should maybe show it. It will be faster too. Right. So. Is this whole? Yeah. Right. So. Let's go here. Oh, so there is this cascade argument. Where simply, but I don't know. Is it enough that I will just explain using this, or shall I draw on the blackboard? It's better to draw. I can.
Can you maybe say again what? I mean, I sort of have lost track. The assumptions of what you. I mean, it looks like what you're saying is just this sort of the second law that generically evolution tends to scramble things. But you must mean something more specific than that. But what exactly is the evolution you're saying?
Arbitrary. Here, this not this.
Yeah.
Allowed operation. It's just arbitrary. You can.
Completely arbitrary.
You can arbitrary unitaries.
Yeah, but I mean, entropy can decrease. It just doesn't usually.
But let me say, so noise operations, arbitrary unitaries, adding a system in a mixed state, maximal mixed state, and removing system. But I consider here that they have the same dimensions. So finally, you have to go back to the same dimensions. That's so now can you say your question?
You're making the spectrum of rho more uniform. Or more
So what I want to say that these operations will make it more flat. Yeah.
But
I want to.
These operations are adjoining a maximally mixed state, removing a random tensor factor, but then doing what?
Unitary on the whole.
A unitary on the whole system. But,
Mhm.
but I mean, aren't there things in that class which decrease the entropy? By carefully.
Yes. If you remove a system, you can decrease entropy, for example.
But yeah, I can also. Yeah, right.
But then you have to add in order to keep dimension.
Right. Yeah, but I can add.
But for what I'm now proving, I now consider this convex combination of permutations, and then for this, then you're right. Yes, here, entropy is all either kept or increased, the entropy. But of course, one thing is that in this approach, we wouldn't like the entropy to be an quantity of interest. We want to get it. So this is sometimes the guide that the entropy well behaves, but we want to get something. So we do not use a priori that entropy is some holy functions that we should talk about. But of course, the guide is, like you say, we should understand what happens to entropy. Yes. So here, for this, it's just the entropy always go up or stays, and this fact is more refined way of saying that.
Yeah.
Yeah. So I just sketched the proof of this fact. Yeah. Yeah.
So you said basically you can reduce fact 1 to fact 2. Is it just
Yeah.
by saying that I can unitarily go from the eigenbases of rho to sigma, and then I just use fact 2?
First, yes, and then you have to also argue that this noise operation can be approximated by these operations. That will be that I'm going to say after this. So maybe I'll say now. Okay, but so good. So what I have on that pictures is that simply is this cascade argument. So you say if I want to go from here to there. So we have that this majorizes, and we want to show that there exists a channel that does it, the convex combination of permutations. So you simply say, first of all, I should diminish this guy. So what I do, I use this primitive. So I mix this guy with this. I use this primitive. So I take this original two levels, I flip them, and I mix them. So then happens what here, that some portion of here goes down to here. So then I take this, I put it here. Now they are equal, but still I am above this. So then I have to repeat the same thing with these two and this third one. So then I can go. Now I really can go because I can really take all of this thing, all of this. I can put here, and already this first one now is equal to this guy. But I did it in such a way that these new probabilities still majorize this. So I can, so I can just say, okay, now I can repeat the process. Now I know that this majorizes this, and I can repeat this process. So this is the Fuhrman understanding of how it goes. Yeah.
Is there a relationship to Earth mover's distance?
To what?
Earth mover's distance, which is a classic transportation problem that takes one probability distribution and tries to map it to another one. And there's a well-known algorithm that takes you from.
It must be maybe this. Yes, I don't know that this,
but I don't know of an Earth mover's distance for majorized distribution. I wonder if that's known. Is that?
I don't know this in this context, so I would need to understand better your definition and then compare. But it sounds.
In Earth mover's distance, you try to find a permutation such that you can take one discrete probability mass function and try to move it on to another one.
Yeah, but if you take just permutation or?
Yeah, just permutation. Yeah.
So then it means that you maybe try to properly order it so that the distance is the closest. Mm.
And it's a well-known problem.
So then, but then there is an issue how to go from one to really to the other, not to.
Yeah, from one to the other, but there's no majorization.
But by permutation you cannot go from one to the other. You have to do some mixing.
And then move the mass down. You try to find the smallest movements of masses such that two distributions can be.
But that's I think some distance. Yeah, that's the same like trace norm distance, and that gives you this distance, no?
It's distance that depends on an unknown permutation.
Yes. So you try to permute this so that it's to minimize this under permutation.
Something like
Good, but still I don't know whether this gives this procedure. I'm not sure.
That's what I was asking.
Yeah. So I don't know. Good. Right. So now we can say this. What already there was a question. Namely, so how we finally prove fact one by saying so it can be actual exercise. Show that that noisy operation can approximate any mixture of unitaries because I can always with unitary go to the same basis, I can talk about classical problems. So let's say any mixture of permutations. And here I'll also consider instead of unitary just permutations. So let's say noisy operations. And in this case will be permutation. Okay. So yes, so you can do this, and therefore we can combine. You can combine these two facts and get that by noisy operation you can so if this majorize, then you find this map, then you approximate it arbitrarily well by noisy operations, and then you get a transition.
Noisy operator is the proper subset of complete positive trace preserving map, right?
Yes.
Yes, and is the fact one true if I substitute it as CPT map?
No, because for example, this any CPT map can, for example, diminish entropy to 0, and these and if initial and final dimension is the same as is here, I should say it. I should add it. So rho and C and sigma act on the same dimension. Then it will not happen. So let's say, let me say these operations are those. So because here you go from some state of some dimension, go to the same state, but in the middle you can have arbitrary dimension, but always you will preserve maximally mixed state. That's a good statement. Yes, they are preserving maximally mixed state. The entropy may go down, but the maximally mixed state will be always preserved. So if you have two particles in maximally mixed state, you remove one. The left one is in maximally mixed state again. So yeah. So but if you allow arbitrary map, then of course you can make the state more pure. You can out of maximally mixed state you can create a pure state. Yes, this is a valid map. You remove everything and bring in a pure state. So in this theory we don't want all operations, all trace preserving maps.
But if it is a unitary, it cannot turn a mixed state to pure state.
Yeah.
Anyway, right?
Yeah. But here the question was whether I can use all trace preserving maps.
Well, the key is
Complete
you're
positive.
only allowed to bring in maximally mixed things.
Yeah.
If you're allowed to bring in a pure state, then you could decrease the amplitude.
Yeah. Yes. And some complete trace preserving completely positive map may be like that you bring in pure states, which here is forbidden.
Here the maximum mixed state is not either rho or sigma, right? It's a Thermo.
Yeah, it's
Thermo reservoir. That is.
yeah, it's something you can consider to be reservoir. You can bring in from the reservoir some systems.
Not them, okay.
Yeah, not them. Yeah, you add like you take rho, you add the rho tensor identity over some d. You can add like this way. Good. So that's it. So now remark is that when you do not have the same dimensions, so when rho is acting on CD and sigma is acting on CD prime, then you apply this fact to and you want to see and you are interested in this question, then you simply apply this fact to this. So that sigma, and you should apply this this criterion to such an input state and such output state. So you should ask whether this is true. And okay. Now so now once I have these general laws, I can do many things, and in particular we can ask, what about drawing work, which means drawing pure bits, So.
To demand this majorization, do you use the fact that the entropy needs to increase during this operation? Is it the motivation that you majorize it because the entropy
decrease?
Just this or that?
This one, yeah.
Yeah. I think that this is just proved, so we start with this. And the motivation for this is maybe not precisely about the entropy. Yeah, in mind you can have this. But because we allow change systems, the size of the system, then entropy actually can go down. So really you should have something more basic than entropy. So the whole point of this Thermo for kids, for adults, is not to start with some definition, with some functions like entropy. We want to get entropy rather than put it by hands. So therefore, we rather think in the resource theoretic way. We say we don't want this theory to be, for example, trivial. So we want that some states cannot go to some other state. And even this restriction turns out that, and we want to have some free state, which is maximally noisy state. So we think more like physically, like, oh, we have heat bath. Heat bath is useless state, so we should be able to have heat bath for free, and it shouldn't produce us, arbitrary work. So we should have such operations that will not produce everything once we are given for free heat bath. And here, this kids version is that we should have such operations that if we bring in maximally mixed noise, then we shouldn't be able to get arbitrary state as an output. And also you can think like that. What kind of states I can have for free in order not to produce everything? You also can think like that. And if you suppose I allow unitary. You can also think like that. I should have some conservation of information. So therefore, I should allow unitaries. And then you say, well, what I can do more in order for theory not to be trivial? And it turns out that, well, the only thing you can add for free is then maximal mixed states. If you add for free some other state, then immediately you are able to produce everything for free. So there is no thermodynamics, no second laws. You have no restrictions.
So the fact 2 is a statement at the level of probability distributions.
Yeah.
So it's not immediately clear how you go from lambda to the statement at the level of fact 1.
Simply yes. So here the thing is that you apply unitary to rho such that it has the same eigenbasis as sigma, and then you apply this classical. So here this quantum part is completely trivial, like completely trivial. But I'm used to the notation simply. I think quantum formalism has somewhat better notation than classical because it is tensor product. And I think in classical probability, when I was a student, I couldn't understand this whole stuff until I learned quantum mechanics and this tensor product. Then I went back to classical probability theory, and everything was much more simpler. So now I want to tell about this fourth thing that I said, namely drawing work, and also forming, like drawing or positive or negative work. So suppose, so I said that work is equivalent to pure bit. So we can say that drawing work would be to draw drawing work m times kt. So that's this unit, and draw m units of work would be equivalent to that, and the picture would be the Szilard engines. So here I use the Szilard engines, and it's very hand waving. So later I will not do such things. Later everything will be defined operationally. So I will not refer to some models that I do not explain. Okay, but for this part of the lectures, it's just let's accept it. So simply so from this you get to this kt ln2, then from this, and that's how this works. But then you can say, well, let's suppose I can do this, but it's on CD, on d-dimensional state. So what I can then do? So yeah, you can also consider some Szilard engine, which is this. You have the cells, and you know that your particle is here. Yes. So then you can say, well, I can then remove these partitions, and I can stick this piston here, and and let it go, and then this Pullman derivations are that is TdS, and this is T times K, and delta S. The delta S is K log 2, and the original, the final entropy would be log D. I don't know where the particle is, and the original was 0. So if I have this state, it's equivalent to this work equal to this KT ln2 times log D, right? But then I can even think of some thing that was in this recent review on this all mostly Thermo of kids, sharp state. I can think of sharp state, which is not a pure state, but it's a state which has, now I write it in terms of probability distribution, so it's some state like that. So here you have some flat distribution and then zeros. So then you again can think, so it's like I have in K boxes a particle, but I don't know where is the particle. So I don't know where is the particle. And then here I know there is no particle. So these are these zeros. And then what I can do, I can remove these partitions. I can remove this partition, and then I can let the piston go, and then I have work which is KT, and this is simply the log D minus log K. And let us note that for this particular state, for this, so the review is by Gilad Gour, Rob Speckens, and there were some other authors. You can find it in archive. So let us note that for these particular states, we have we have the situation that we have the following situation, that simply how to say okay, let me say like this. What will be now drawing work? So drawing work would be this. I want to go I'm going to say this. So from sharp state, you can get this amount of work, but you can also form sharp state by this amount of work. You just start. So you have converse. So sharp. So now we have some work, and we go to sharp state. How we do that? We simply have these partitions. We don't know where is the particle. So we start from scratch, from completely flat state, and then we say, well, okay, so we just remove this partition, and we introduce the piston here, and we move it to here, and then we insert. Then we know the particles are only here, and then we insert these. So these partitions we already have. So insert then this. We insert back this partition, and then we know that particle is somewhere here, but not there. So we have formed again this state. So this state is like equivalent to work, and it is like generalization of what I said before, that one bit is equivalent to KT log to work. So sharp state is really if I have a sharp state, like K sharp state, so K with some K non-zero values, so then it is really, we can say it's the same as having this amount of work. KT log K, right? So then So now drawing work is I go from raw, and I should get the sharp state with the largest possible k. Oh, sorry, the smallest possible k. Possible k. So you see, so this is completely information theoretic question, and then I will multiply it with the results. I will multiply it with this kt log 2. So then this is really going from some state to some other state. So you can apply the majorization. So you can say, but this is equivalent to this, and now, so in our case, it's a sharp state. So k sharp state. Right. So let's see what we can do. What is the largest k? Oh. So we want. So this row has these eigenvalues p1 to pd, and we want this to majorize this sharp state. Right. So what does it majorize? So it means that p1 must be greater than 1 over k, p1 plus p2 must be greater than 2 over k, and finally we need that p1 plus pk should be greater than just 1, because we are already here. Sum of these is just 1. But this means that all these other p's must be 0 for I greater than k. So our p, so if this majorizes this only if we have this situation, 0. So the state must be like that, which means that rank of rho must be less than k. But then you see, if this is so, then you can find that all the other conditions are satisfied. So it turned out that this is equivalent. So as you easily see, so this is equivalent to rank is less or than k. Question. Right. So you can then nicely say, you can introduce the. Okay. So it means what? So it means that this smallest possible k must be greater than the rank. So it's rank. So we prove that we can go from rho to the sharp state with k equal to rank of rho, maximum number of non-zero elements simply. And then we can say, okay, so then we do our multiplying with kt, and we get that therefore work that we can get from state rho is, and now we can write it the following way, so it's log d, but now log rank, so it will be log rank rho, but this is a name, so it is mean entropy of rho, right? So we obtain that this work of extractable work, let me say, extractable work is just this given by this formula. Then you can do another exercise, and you can consider the converse direction. So you want to form, and then you get that. Yes. So you simply ask the sharp state with now the largest possible k, with largest possible k to rho, and this will give you work of formation. So it's the work that you need. So it is this direction. So that was from rho to work, And this work formation turns out also is nice. Is log d again, minus, and here is h max of rho. And this h max is a nice.
Just chalk it down below.
Yes, thanks. H max is what? Of, say, probability distribution, but it's the same about rho. So it's minus log, and this maximal probability maximal element. So P max is maximum over all IPI. So take just the largest element and the minus log. So in this, yeah.
Michal, aren't these H max and H mid usually defined the other way around?
Maybe. Yes? Terrible.
Exactly the other way.
Terrible. Sorry. I always confuse this. Yes, H max, because relative entropies will be the other way around. Yes, relative entropies. Like relative entropy that is related to this will be D max. Good. Yeah.
If I understand correctly, in order to get work, you have to remove a pure state.
To get work,
Yeah, if I want.
you have to produce, and I made it a little bit more deliberate, a little bit more complicated. So here I said, okay, initially work is just a pure state, but I then showed by some zero entity that you are happy with the state that is not necessarily pure, but has some flat here, some flat part. But you say that essentially the point is that you can reversibly change this state into work and back by use of these engines. So essentially, initially I said, oh, pure B is such a thing, but also you see that also such a state is reversibly interchangeable. You can it's like it can be served as a definition of work because you can go there and back. So finally you say, okay, I want to produce these sharp states, and these sharp states are equivalent to work. You also have some questions.
Yeah, here you take the case where k is equal to rank rho, right?
Yes.
So if you take k bigger than rank rho, what wouldn't it be the same?
If I take bigger, yes, I can, but I would like to extract optimal amount of work. So I really want smallest. I want a sharp state that has the smallest number of these k's. Then I get more work. The more pure, the more work. Yes. So I want the purest of this sharp states. So essentially here, work is purity. I want the most pure output as I can get. And here, so this is.
But it would it be the same result, same formula? Or would it
for pure states?
no, yeah, but k is greater than rank rho.
No. Then you can get. Let me say, from rho you can get also arbitrary sharp state with k greater than rank rho. Yes. Yeah. Yes. So this is the smallest rank sharp state, but you can get all the others that for k greater. You cannot get k smaller.
I understand. Would it be the same?
No, because then work will be smaller, because if k is larger, then the work is small. Because the work is log d minus log this k of the sharp state.
Same structure. Okay.
Yeah.
But less.
Same, but it will less than log rank rho. What's the question? Good. Right. So. Okay. So what happens here is this. So we see that we have irreversibility. So so we have work of the that I can extract is much smaller very often than work that I need to form the state. So we have this gap, irreversibility. Yes. So I go from let's say I create a state, and then I get some work. I create, and then I want to get some work back, but this is smaller than this, usually. Good. So this is very rigid. I present everything very rigidly. So you say, well, but that's very rigid. That's very non-physical. If you have rank rho is the quantity. What about if instead of zeros I have 10 to the minus 6, yes, or 10 to the minus 40? So yes, what you do then, you simply say, if you are going to accept some probability of failure, epsilon, then you simply should do this, that you you will not produce this very sharp state that has zeros here, but you're happy that this state has here some epsilon. So, which finally boils down to the fact that you will not here put rank of rho, but rank of a state that is close to rho by epsilon. So you will simply try to find the essentially you would do this, that if you have a state, then you would put here the smallest elements, and then you would compute, which add up to epsilon, and then you compute this rank, right? And then you say, okay, from this you would produce your sharp state, and then you say, okay, with this I have to live, but that's the probability of error that I accept. So this is this whole smoothing. I said it in 30 seconds, but there are tons of literature on this, very difficult things if you want to do some more complicated stuff.
Does that mean that, I mean, if you accept the probability of error, does it mean that sometimes you get that much work and sometimes not?
Yeah.
Or is it you get a little bit less work and...
No, it's better, more safe to interpret it that you with some probability you get work, so and with some probability you simply fail. You may even be you may lose work. Yes. So with the piston, it may be that instead of you will need some force to throw it in this direction. So with probably epsilon, bad thing may happen, and with probably 1 minus epsilon, you will get this work that you wanted. So the formula will then be that you put here epsilon, and the formal definition is that it's you simply and here you have to be careful with this formation distillation. Let me say about distillation, about formation. This may be exercise how you should define this epsilon in order to be sensible. So here it's simply you try to minimize the entropy for the states that are close to my original state. Yes. So you do not look at the rank of your state, because that's not very physical, but you look for the rank of states that are close. So you simply cut tails. So it's about cutting tails. Good. So in this situation, the smoothing is easy, but it can be very difficult in some more complicated scenarios. Right. So we have this irreversibility, and we can now. So this is the single shot, some single shot results. Well, you can say, what if I now you know that thermodynamics is reversible in this macroscopic picture. Yes, you have a reversible Carnot cycle. So you should be able now to make some macroscopic, some thermodynamic limit. So, well, in this again toy scenario, say so. Suppose if I have many copies of rho, and I want to go to many copies of sigma. What I can do, and the result is that then you regain reversibility, and that the work of formation and work of distillation, of extractable work and work of formation, are equal, simply, and they are, you guess of course that they are given by standard entropy. But before saying that, let me rewrite these final results in a nice way. So, namely, one can notice that one can introduce. So one can introduce two kinds of relative entropies. One is this, which I already told you yesterday. I use this symbol S. For some reason, people very often use symbol D for relative entropy, so I will mix the symbols now, and they will be really mess. So so yesterday I wrote this relative entropy. You can also consider this other relative entropy, which is such a thing, Pi over Qi. And it turns out that you can rewrite this work of formation and distillation, extractable work as the mean, or KT, the mean log n to the mean of a row with respect to maximally mixed state, maximally mixed, and a raw work of formation is the opposite. So is this max, the max quantity. So you see, you have two different relative entropies, and then in this Thermo for adults we will have just the same relative entropies, but here we'll have Gibbs state. So you see that this is indeed a special case of that thing. Okay, and now I go back to this. That was item 3, I think, to IID. Namely, you simply say, well, you ask, so what if I have many copies and I go to some output state and I want this output state to be epsilon close to and now I can even take these pure bits. It will not make a difference in this. So here normally I should maybe sorry. General question is this. Sorry. General question is this. That's the general question. Okay, so I assume that epsilon will go to 0 with n growing, and find the limit of m divided by n, right? So it's this question, and it turns out that in this question you simply regain reversibility. And how you do that? So you simply say, first you consider a pure state, right? So of course almost. So the output is so you have raw out, and here you have up to epsilon. It is this thing, right? And you get that this limit of this thing is simply equal. You can get it to be equal log d minus s raw. So now here you have this already standard entropy. So it will be somewhere in between. Somewhere here, it's great. So the work of so then you say that the work per particle is it's times, this is the ratio. So the extractable work per input state. So the extractable work per input state is this log d. Okay, but this is also from n copies, which should be compared with this log d minus this horrible here thing. So this is very often small, while this is this is standard entropy. Yes, so I should write it. So I mix here. So it also can be like this denoted, and it's just minus sum over IPI log pi. Good, and also so that's the extraction, and then you have also formation. So you start with this, and you go to this, and you go to this, and you then again ask what's this thing, and you can make it simply the same. So final result is the following: that you simply, when you go from raw to sigma, then what you have, you can split it. You can first go to this thing, and then you can go to here. And therefore the ratio, n, and some m. So here some k, some m. So the ratio, final ratio will be m divided by k, k is divided by the final thing. Okay, and k divided m, yes, so this is given by this, so this is a distillation of work, so it is given by this log d minus s rho, and this is the opposite, the 1 over this thing. So it is minus s of sigma. So finally you see, and also, of course, it happens that this quantity is actually relative entropy, standard relative entropy from the maximal mixed state. So you can simply write this as a ratio of relative entropies. Right. This one who is interested in entanglement theory and who knows something about this sees this whole thing as a completely trivial from the point of view of difficulties that are there, and these results are, you can think they are special cases of this theory. You maybe have to do a slightly different thing, but it's this happens. This is relevant for entanglement of pure states. So the difficulties here are much smaller than there, and this is reversal. Asymptotically, you have reversible theory. You have just one parameter that describes everything, which is an entropy. So look here, we've obtained entropy. Yes, we didn't put it by hands, but we've got it, right? As from resource theory. So we assume class of operations, and then we obtained the entropy as a limit, IID limit. But we have much more because we have also this non-IID, and then we do not have relative entropy, the standard entropy, but we have this H min and H max, and they are different. So here we have reversibility, and in general we have irreversibility.
So this whole argument relied on our fact 1, which is that using the noise operation we can go from rho to sigma if and only if rho measures sigma. Intuitively thinking, I think I agree with the one direction, but I think the other direction is probably perhaps not as intuitive. For example, majorization condition is quite strong. So why is it the case that it has to be majorization?
Once you so ask whether in this fact whether
So if the rho majorizes sigma,
can we
perhaps we can do the only use the noise operation.
And that
So why is the opposite necessary?
so when there exists an operation that how is that they have to majorize each other? So it comes from this fact 2. Because if you can make if there exists a noisy operations, let me see.
If I can, I think is why are noisy operations only permutations of probability? Why can't they be?
Oh yes. How is so? Maybe you're right. Maybe I skipped something. So indeed. So then you see. Let me see. Right. If I can, how is it so? If I can go by noisy operations, yeah. So I built only one direction. So the other is if I can go, then no, it's not about how it's so. Okay, let's find it. how it can be. So good, thanks for the question. so suppose we have, suppose there exists a noisy operation lambda such that we go in this, so that we are, and then we we ask this. So we ask, and then we want to know that sigma, that rho majorize sigma. Yes. So essentially, we ask this: whether is it true that we ask this question, right? Good. So, and this you simply check by hands because but you also assume that this noisy operation is here. You assume that initial and final state have to be of the same dimension in this. So we assume that this lambda brings u to the same dimension. So so you have this. So but you can go through different dimensions. So unitaries preserve. If you're unitary, then each step you preserve. But then you have this. So let's say if you apply unitary, then of course you have how you want. Then you have this, but also in the other direction. So you have some steps. You have row 1, then you have row 2, which may be on a different dimension because you may add some stuff. Yes, so it may be some d1, d2. Then you go and then you go to row 3, to row 4, and finally you have the output, which is again on the CDN. Again, CDN. But normally when the lecturer cannot solve something, he poses it as an exercise easy for students.
John Driscoll asked a similar question in his course this year. Can you use like the GGHW section? Does that seem familiar at all?
Right. So which theorem?
The Horn-Booters theorem.
Aha. Good.
Let me pull this up. Avoid changing dimensions by giving auxiliary pure states to rho and sigma on both sides the same one. And then no pure states.
No, better mixed, but the right direction, yes. So we should consider simply to begin with very big mixed state, and then we do not need to add. So
It's not obvious that if rho majorizes sigma is identical to rho tensor mix majorizes sigma.
yeah, so that's the fact we need.
But if I put a pure state there, then majorization seems to be preserved.
But we cannot answer. Yes, but for mixed states it's true. It's true.
My operation, I'm just saying, if you can if lambda can go from rho to sigma, then there's another noisy operation that can go from rho tensor 0 to sigma tensor 0. I just not.
Mm-hmm. So it's like, but you will then regain these pure states.
Yeah. So
Yeah.
I'm showing them essentially I'm deriving the same thing with the tensor 0.
Mm-hmm.
And this noisy operation can then use some of these 0 things as oscillators.
No, but that's not so good. No, yeah, may use up. But if you multiply with identity, then with maximally mixed state, they do majorize. I think this is the thing. So you can you have majorization. Yeah, I think this is the way how we proved in the paper. Yeah.
Can you just say, I mean, what you can see is if you start with low and maximum mixed state, then it has to stay in maximum mixed state because you can just add maximum mixed state and they have to be preserved. You can't do anything on the maximum mixed state, just that you
Yes.
have a doubly stochastic
Mm,
operation, not in the classical sense, but in
yes, but then there is.
and then you can say, okay, I can use unitaries to bring this.
But then there is a problem. Yes, so you have a quantum doubly stochastic operation, which we know is not the same. It's larger class than mixture of unitaries. Aha. Oh, okay. So maybe there is so. But it doesn't work for the quantum case.
No, it doesn't.
Yeah. So. yeah. No, if you already have a class of bistochastic matrices operations, then I think you are dead, because then you don't know how they look like even. Yeah, so one way is really multiplying with a big mixed state, so this preserve, and then you will only act with some unitary, and later you trace out. So this one thing, and the other, I think there was simply a paper on that. Ullmann proves the theorem, just about, I think, doubly stochastic. But how he did it, I don't know. I never seen the proof. I have never seen the proof. So good. So thanks for the question. Yes, I completely have disregarded this problem. Yes. Right. So yes. So yeah.
Don't you see like this? You are dealing only with mixed states with one about d, each one with different dimensions. So couldn't you see like as artificial reduced state of a bipartite entangled state, yes? Maximally entangled state, but with different Schmidt lengths. And then you would obtain this entropy because they are the unique
measure of entanglement.
For pure.
Yeah. So when we did the proofs, it turned out that you somehow use a little bit different arguments. So, for example, in the proof of uniqueness of entanglement measure, this here the one way is the compression. Here is essentially this is compression. You simply compress it using some Shannon compression or Schumacher for quantum. Namely, you find some subspace on which this state sits, really. So this argument here is used for extraction, while in entanglement theory it was used in the formation for some reason. It's kind of funny that we didn't have the direct. When we look at the proof, they are different. Maybe you suggest even not to look at the proof, but apply the results. But this I don't know how to do. So rather, I would think you can just use their proofs. But it's
using this compressed data.
Yes, but it turns out that they use it for formation, we use it for distillation, and vice versa. So it's like it switches. Maybe it's good to understand it better, because yeah. Mm-hmm.
Just so John's class, it's not the Horn Luther's theorem. Horn's on the other direction. It's the Houston-Joseph Luther's theorem, and we basically prove this. And so you basically use that theorem. It says that you can write the density matrix in terms of like some other basis, and then you take the norm on each side, and it shows you that you have a matrix which is going to be doubly stochastic.
So under NW, so you say for doubly stochastic, these K-fan norms are simply monotonic under doubly stochastic maps. Which kind of norm? Yeah. Good, but yeah. Good. Well, how much time I'm left?
10 minutes.
10 minutes, good. I realize that today I have no jokes prepared, and it's so late that I should have many in order to waking up. Right. So okay. So we are done with Thermo for kids for a while, just for good. We're done. Maybe I should give a. This was actually the exercise to do this. So I should maybe give a hint. The hint is to use typical subset. So maybe who is interested can either find it or ask me. So now I will simply sketch the beginning of this Thermo for adults, so that tomorrow not tomorrow, but later I will be more prepared. Good. So for So here we start with operations. Yes, so operations. Well, maybe system. Maybe we just start from a system. So here, system. So we assume we have a heat bath. Heat bath. Then we have a system of interest, and then we have some work reservoir. And for work reservoir, we want always to be in a pure state, pure excited, a pure eigenstate of the Hamiltonian. So we have total Hamiltonian, which is this. So it's like non-interacting Hamiltonian. Then you imagine that everything interacts, and then it parts. So, and the effect of this should be some unitary, that in this rigid scenario it commutes with this Hamiltonian, which makes we in this way we make sure that we do not add energy from somewhere. So it assures energy conservation. So our operations are like this. Are unitaries on the full system, acting on the full system such that they commute with this stuff. And so that's this. Of course, adding any system in a Gibbs state, and no removing anything we want, removing systems. So you see that this is a conservation energy which is related to first law, and that it is unitary is basis for the second law. So this is conservation of information, that is unitary, and so we have already. We see where should be the origins of the laws, and what the general question we ask. So that's operation. Now, what is drawing work? Work. Definition of work. So as I said, we define work in this way that we start from some state, initial state, and here you have some. Maybe here I say it in more specific way. Namely, we start with some let me write what is enough to have. This work reservoir, it's enough to have the Hamiltonian, that is just this thing, where this W will be tuned to your needs. So essentially, we have two-level system with some given energy, and we call this width. So it's work bit. Of course, you may be more interested in having some universal work reservoir to which you can store work in from many different processes, but it is also fun to know that for any process it's enough to have just two-level system here to get this work. And in this approach, it's natural to take just this two-level system. But as I say, if you take much more complicated, you get the same. This is proved. So I will just stick to this. So we obtain work. We obtain work W if we simply have some maybe output state, which is some I don't know what, and then here we go up to the excited state, right? So so we drawn work W, and so that's about drawing work. Now you can say you can maybe want to specify such a thing that you, for example, go from a state and you put some work and you get say sigma. So it's in this picture you see it because that's the initial state rho. And then here, this is the final state sigma on this system S, and the work, and you obtain the work W, but you can also if the work is negative, then this means that you simply put work W. So you see that everything is about state transformation. We have some state, and we have some final state. So essentially, again, the question you have to answer is just, can I go from one state to other state? Right? And then the question related to drawing work will follow from that. If you have this general result, then you can get other results.
Sorry about the notation. Why is it rho plus W goes to sigma if you actually get the work?
Yeah, in this case, you're right. That's this thing. So if this W happens to be negative, then indeed, then this means actually, then this means the same as this, yes? Because if you just get an output state in a lower, so then it's in a lower register. So then this means that you have put the state, put the work. But if this is positive, meaning this is ground state, is excited, then yes, then this is that you obtain the work. Right. Good. So I will manage maybe to. So, yeah.
When you say that you can add any system in a grid state, are you assuming that somehow the reservoir is a discrete particle with no interacting Hamiltonian, like that have many particles and it's H plus H plus H?
Well, not necessarily. So maybe you can think that you simply, apart from these systems, that this system can grow. So, for example, you can bring in new systems and. Yeah, you're right. Yeah, so the system that I bring should be yeah, it's better to think that the system that I bring are a product with this whole thing. Yeah, so you can think this is a big heat buff which may be interacting but has some properties of a heat buff, some generic heat buff which is big. But then you can also bring some systems that are independent of everything else in order not to have a arbitrary Hamiltonian. Yeah. So you bring H1, H2, H3 arbitrary systems with arbitrary Hamiltonian, but should be in a Gibbs state. Yeah. Yes. In the same temperature. Everything, there should be the same temperature. If you would bring Gibbs state in a different temperature, that's already not a Gibbs state. So you can then, of course, your theory will become trivial. You could simply run Carnot between your systems with one temperature and with the other temperature. I know what you mean, but let me just answer. Yes, for example, if you have you can bring arbitrary Hamiltonians, but according to the same temperature. You mean this? So, for example, I can have this, and the levels are. So let me say, and here, like almost only here populated. So that's a Gibbs state. So you have here large energy, and here you have small energy level. And so what I mean is this: that this is a Gibbs state to a temperature, and this is a Gibbs state to the same temperature, but there is different energy. Yes. Now what you say is, I can think of this. So what I can have? I can have different temperature, yes, and I have this Hamiltonian, but because I have different temperature, I can have the same populations here, right? So that's the thing, right? So you are not allowed to bring this, right? So you can bring because this is not a Gibbs state to this temperature according to this Hamiltonian. So you take Hamiltonian, and then you have to really bring this state that is. You have to bring a Gibbs state for this Hamiltonian. So you cannot bring a Hamiltonian and then arbitrary populations. No, the populations should be of the Gibbs state to this Hamiltonian. So essentially, your state that you is maybe physically a state that you bring in must be in equilibrium with your heat buff, and heat buff has temperature T. So you can imagine that apart from this, you have a zoo of other systems. So you have this. So let me add them. So you have some other system 1, system 2, right? And now this is your system of interest. This is your state that you will manipulate. And these are just Gibbs. So these are Gibbs states. V1. So you, in principle, you can, in what follows, I will actually use only this. But sometimes it's convenient also to add some other, and they have different Hamiltonians. So ultimately, if you want to have whole big picture, your Hamiltonian would be HR plus HS plus HW plus H1, H2 plus or arbitrary number. Like there was this and.
So basically, if you look at all these other systems, can you look at all these other systems as part of the?
Yeah, you could also look like that. That this heat bath, but for some clarity, maybe you want to have them product with the heat bath. But this is enough to say that this Hamiltonian of the heat bath has some non-interacting parts. Like it'd be you have some systems that are in the heat bath that, they, for example, do not interact, so they have separate Hamiltonians. For many things, this is not needed. The generic heat bath is enough. Yes.
Can we, just by the unitaries that we have, assume that if all these SI have the same temperature, that they also have the same Hamiltonian? Or that they give states to the same Hamiltonian? Because we can just unitarily rotate?
No, because this unitary has to yes, then sure. If I add systems, my unitary should commute with the total Hamiltonian. So maybe this is not very fortunate. Yes, I should say to the total Hamiltonian when I add these S1s. So or you just say total Hamiltonian, right? When it is really needed is when you want to have the final state with a different Hamiltonian than original. So then you have to change system, or if you don't want to really have time-dependent Hamiltonian. So then that's why we use this. But suppose we want just to go from some state to the other state and keep the same Hamiltonian, then this is not needed. It's enough that you have a heat bath. Good. So perhaps it's the end. Yes? Or
You should finish up.
yes. So thank you.